Okay, now we will look into some kind of an analysis which kind of shows us that yes, the algorithm does work, and it's not that it's doing something which is completely random, completely arbitrarily. Otherwise, anybody can write down an algorithm, especially when I've allowed you all styles possible. So we've got a function fx is equal to something, and for the time being, how much maximum can I plot? Can I plot this function? I can plot it if it was one dimensional. So let's take this function as one dimensional, and this is what in one dimensional this function will probably look out to be. So that's fx, and this is x1, and I'm assuming that it's one dimensional. And over here, this is what's called as a local optima. I've drawn it for the minimization problem, so it's actually a cost function. And this is what is the global minima or the global optima. So our problem is to get this solution, which is the one that has the lowest cost which is possible. And how do I do that is what is, of course, the exercise for me. Now, I can actually draw this thing in two variables as well to make it clear. So let this be x1 and let this be x2. Now I need to draw fx, which will be the axis coming vertically outbound to the monitor, but if I use a contours, then I can draw it up. So these are the contours. These two have the same fx value, these two have the same fx value, and that's what the contours look like. So again, let's say this is what is a local optima, and this one is what is a global optima. And this is the one that I need to find out. I need to find out this thing over here. Now we started off with a discussion that I can always take a gradient and solve this problem. What is the problem? So the problem is that that's the individual. I go in the direction which minimizes the gradient. So I go up till here and the gradient is 0, so I stop moving. And similarly here, I go perpendicular to these contours, so I'm going perpendicular to these contours. Here it was here, so I'm going perpendicular to these contours, and I go here. And then I just stop. So they get converged into local optima. So let's write this thing down, that local gradient based solutions like the backpropagation algorithm for neural network learning, they get stuck at the local optima. So it's not the solution, and because it's not the solution, so I'll have to do something about it, and I will have to improve that up. So we use population-based method, of course, the genetic algorithm, and what it looks like is I have random individuals which are around over here, and I've got random individuals around over here. So the first operator was selection. The fitter individual gets selected multiple times. Remember, this is the closest to the global optima, but it's not the fittest. The fittest is this. So this gets selected multiple times, then this, and then a few times this. But then I said there has to be some probability that worse individuals are also selected. Otherwise, if this individual dies, then I'll probably never come over here, and similarly here. So the fittest individual is actually this one. It's not this one, which is closest to the global optima. So they get selected multiple times. The first thing that I do is a crossover by pairing. So let's say that these two got paired and they produce this individual. So the children of these two, and then these two mate and they produce this as the two children. So the red ones are this thing. And then I apply a little bit of mutation. So that's just a random noise in a random direction. So the arrows are the one which is a random noise. So again, these two get selected. So that's children. And then I move them up a little bit. So let's say these two mate. So these are the two children. And then I move them up randomly a little bit in any direction possible. So I just apply a Gaussian noise. So I move them up a little bit. So that's what's the crossover and the mutation. Now, in all the individuals that we looked at, the children were getting formed in crossover intermediate to the parents, and in mutation they were just moving in any direction. It could be in this direction, in this direction. It could be here, 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 here. It could be absolutely in any direction which is possible. And that's how the algorithm goes. So let's delete the ones that did not get selected. This did not get selected. And in fact, let's remove all the blue ones. They are the parents. It's not the parent and these children are fighting among themselves. So that's the one that happens. So there are some new individuals which are after mutation crossover here. And similarly, these two will get selected and they'll have individuals, probably one around over here and another one which is around over here. And then they'll move a little bit. And similarly around over here, all the blue ones can be removed and the red ones will move around. Now, something interesting that happens over here is that this parent has produced a child which is still competitive. So it's got a better fitness value. And in fact, now its fitness value is comparable to the old parent of this one, although it has produced new child and the new children are still better. So let's copy this figure once more. Remember, this is the global optima and this is what my new population pool turned out to be. So these individuals are showing tending to go on the global optima. And then there is this individual which is not as good. Now earlier I only dependent upon luck for this individual to survive. Now even if I select a few individuals, so let's select a few individuals. So this will get selected multiple times, but this is also good enough. So it will actually get selected multiple times. Now it's competitive. In fact, it's the third best individual. So now this will cross over twice. The first one between this and this, let us say. And they'll move randomly. So let's say this one. And the second time, let's say between this and this. So the first individual gets generated here and the second one gets generated here. And they move randomly. So great parent produced two children. One of it was worse, but the other one turned out to be better. And similarly for all, these will produce pair in and produce children. So these won't get selected. Or let's say one individual here gets selected, which produces children, let's say here and here. So in the new population pool, what you see is now you've got another individual which is even more competitive. You've got lots of individuals. You've got another individual which is more competitive. It produced two children, last time luck favored, and this time out of two children, one got better. And there are individuals which are almost at the local optima, and there are too many individuals here because they got selected many times and mutation made it even better. Here there's a sole surviving individual for some reason, and there are some individuals other places. So maybe there are a few individuals here. Now this becomes the best individual, which means it gets selected multiple times. Now it's the best individual. It's the globally the best individual. It gets selected absolutely multiple times. And because it gets selected multiple times, there are fewer individuals here that get selected. Now this and there are a few that get selected. Now this crossover mutates multiple times, so it got selected 3 times. So let's say that it produced 3 offspring, out of which 2 are worse, and then again 1 is even better. But or let's say 2 of them are better. It got selected 1, 2, 3, 4, 4 times. So 2 got better and 2 are worse. And here also 3 individuals got selected, so they produce in some children. And that's the one that gets made. Now these 3 individuals will together get selected multiple times. Let's say this 2 times, this 1 times, and this gets selected only 1 times each. So they'll produce even worse children. So let's say here after mutation and here after mutation, and these produce more children over here. And that's the one that gets formed. So these are the individuals from mutations over here, and let's say both of them are here. Now you see that all these individuals are significantly better than this, so they'll get selected multiple times, and none of them is going to get selected. So the population that you are left with is only like this. And they'll get selected multiple times, and they'll go more towards this thing over here. So if you look at it, starting from here, what did we do was, earlier the local optima, each one of the local optima had a lot of population, and this was seemingly the best. We had luck favor us once, and this individual, which later on developed better characteristics, survived. Once it survived, still this was the best, and it was attracting a lot of others. So the population density in extremely poor local optima got reduced drastically, and this what then appeared to be the best place on Earth. So as per current knowledge, this was the best place on Earth, got survived, and luckily this became competitive. Some positives of this bad characteristics over here, it was at a bad area over here initially. It was the 5th or the 6th best individual. They were extremely competitive individual here, but once it survived, then it reproduced more, and then the individuals explored more. Eventually it got into regions where it could challenge this optima, and the moment this got challenged this optima, this got into a region which was better than this one. These individuals got to reproduce more, and these got eventually eliminated. So their population density kept on reducing. So many when it was the best, to a few when this was the best, to scanty when this was the best, to none when this was the best. So eventually all the individuals come around over here. Now there'll be a competition between these. These will reproduce more, these will reproduce less, and therefore you will see that eventually all the individuals are going to be here only, because the moment they step anywhere else, they get unhealthy and die off. And this thing is called as convergence. Convergence is when all your individuals are into one small region, when all your individuals are at one small place. That is when we say that the algorithm has got into a convergent situation. So this is what is a convergent situation to us. So if you ideally see this, writing down as text, so the individual were initially spread and there was one individual at the modality which had the global optima. So every crest and trough is called as a modality. The first modality, the second, the third, the fourth, and fifth. So every crest and trough is a modality. So luckily, That individual survived. And by mutation, or let's say crossover slash mutation, soon became promising, became competitive. That's the next thing that happened. So it soon became extremely competitive. It was better. So it proved its worth with time. And hence started getting selected multiple times. Now when it gets selected multiple times, produces more offspring. Some of them will be bad, but few of them will be good. And luckily, some of the offsprings were better. As it became best individual, it started attracting all others. So when it became the best, then you saw that it started attracting all of them. It was reproducing more, the others were reproducing less, and the others were dying, it was surviving. So soon population density at other optima reduced eventually to 0. And global optima modality had all individuals. So soon all the individuals were only at the global optima, and then we said that convergence happened. Later convergence happened. So how a general genetic algorithm operates, so initially the population is random, and slowly they get attracted to each other, slowly they get towards each other, slowly they try to go towards each other. The ones which are so far the best get more offsprings near that region, the ones which are further away get lesser offspring. So this got initially more offspring because it was a bet, and these eventually died. This luckily survived. Then this got more offspring because it was competitive, and these died. So these almost died. This got more offspring. When this became the best, then it attracted more, so it reproduced more, and these reproduced less. When it was the best, then it reproduced more, and this reproduced less, and then it was the only one. So if you think about it other way around as well, so there was a time networking was hot, so more people would do networking, less people would do AI and machine learning. In fact, there was a time when electronics was hot. Everybody would do electronics, less people would do networking, AI, IT. Then some discoveries happened in IT, and suddenly it was a boom. So the number of people in electronics slowly started reducing, and IT, electronics started reducing, and networking became hot, AI became hot. In IT also, networking started attracting a lot of people. Then suddenly some discoveries happened in AI, and suddenly networking people started reducing, and machine learning, they started increasing. So whatever looks hot attracts more people towards itself. Whatever looks not hot, it slowly reduces all its population. That's exactly what the genetic algorithm has done. And that's also how we solve problems. So starting over from an initially random population, we get all the population at one place. You can do exactly the same thing here as well, not shown. So eventually just a few iterations. So if this survives a few, and I get in a few individuals here, so suddenly this is hot, so this will get a lot of individual, this will get only a few individual mutation, and this will get very few. So then what will happen is that these individuals are now competitive, so they will still have some evolution. This is still hottest, so it will attract a lot of individuals. this is not at all competitive, so population will die off. Now suddenly these individuals have gained a better value as compared to this. This is hot now, so even though population density is bad, but this is the fittest individual in the entire population pool. So this will die off, it's bad. The population density here will reduce and the population density here will increase because this individual is the best. It will get selected most of the times, and eventually these will die off because you get too many people here of great ranks which dominate, so eventually you'll get all the individuals here only. Here also the further away areas children will die and nearer ones will survive, so it will get right into it. Now convergence is, if I draw a hypervolume around this space, you see the hypervolume will only reduce. So this is the volume within which all the individuals are to be found, and you see that this is continuously reducing. That's convergence. Similarly here, if I draw a hypervolume, that tightly covers all the individuals, you see this volume will only reduce, and eventually when it will come to convergence, so you'll have all the individuals here only where the hypervolume is here. That's when convergence happens.